All right, so today we're going to talk about the last of the three heat transfers, which is radiation. And so it's interesting because at a fundamental level, all the heat transfers basically operate the same. But most heat transfers from this fire that you're observing is through infrared radiation. The visible light that we can actually see with our eyes, although it's dramatic and kind of cool to look at, it transfers relatively zero, well, not zero, very, very low thermal energy. Convection transfers energy away from the observer as hot air rises, and conduction is negligibly slow here. Skin is very sensitive to infrared radiation, so you can sense the presence of the fire without looking at it directly. Today we'll talk a little bit about electromagnetic radiation, and so the transfers are slightly different, but they're similar. And we try to categorize them. And as I mentioned with the fire, sometimes you have all three taking place, right? Which is usually the case. But some types of heat transfers, you have more conduction than you do convection, or more convection than you do conduction. And the formulas are pretty much the same because of the relationship between heat and the different types of energy, right? Because sometimes we transfer to kinetic energy, and the kinetic energy can give off heat. And now electromagnetic radiation is really light. Okay, so this all has to do with electrons. Whenever I say electromagnetic radiation, I'm really referring to light, and that's beyond not only the visible light, but as we mentioned here, infrared. So what does that mean? Well, if we go here to the next slide, essentially light, and it's hard to describe without going into like electromagnetic radiation and stuff, but basically there's a visible spectrum of what we can see. So visible light, what we can see, visible light, we talk about the wavelength. So the wavelength is always written with the Greek letter lambda, and it's in hundreds of nanometers. So lambda is a fun one to draw. I always do this little thing and then do this. And so that goes anywhere from 400 to pretty close to 700. It's actually more like 650 or something like that. But just to kind of keep you guys on the same page, it's around there. And that wavelength is nanometers. That's if we think of light as a wave, right, for it to complete one full cycle. And so what you see here is that once you get beyond this, right, so this is like 400, it's really more like 650, but we'll say around 700. Okay. Once you get beyond that, then you can't see. So UV light, like when you get sunburnt, this is from the sun, UV light is lower than that. IR, if you do red light therapy, is lower than that. But basically, the intensity is based on the color. So here we have white, right? So here, and let me change this to a different color. The different colors in a flame really represent the energy and also the wavelength. Now the wavelength is inverse to the frequency, and this has to do with electrons. So Basically, matter absorbs heat energy, or in this case, light energy, or gives off light energy. And it does it in a frequency. So if it gives off the energy slower, that might have an impact on the wavelength, and then the wavelength impacts how we could see it with our eyes. And then as the color changes, this is also energy. So what they're saying here is that our visible spectrum has a lot of intensity, but something that's white hot, this is a temperature, and then this is what we would call red hot. So as you can see, white is much hotter temperature-wise, and so this is like 6,000 degrees Kelvin, and this is 3,000 degrees Kelvin, and then you have this area here in the middle, right? And remember that thermal energy is energy, okay? So what does that mean? Well, a graph of the spectra of electromagnetic waves emitted from an ideal radiator at 3 different temperatures is what we're looking at. And then so the intensity or rate of radiation emission increases dramatically with temperature. And so then the spectrum shifts from visible and ultraviolet parts of the spectrum, right? This is based on the frequency. So the shaded portion denotes that the visible part of the spectrum, it is apparent that the shift towards the ultraviolet and temperature makes the visible appearance shift from red to white and to blue as the temperature increases. So what they're saying is this, I should probably mention, frequency-wise, here at red hot, this is a higher frequency, so our frequency, our wavelength is greater. So when it's red hot, notice that our wavelength is around 2,500 nanometers. So this is about 2,500 nanometers if it's red hot. But that's not what we can see. What I can see is just this right here, okay? And then what we're doing is the more energy it has, the more that the wavelength shifts towards the blue side. So this would be kind of like blue, and this would be red. And then the next thing would be infrared, which is IR. That's what this IR stands for here. And so what they're saying is that it's apparent that the shift toward ultraviolet with the temperature makes the visible appearance shift from red to white to blue, and then the upper part of the flame is orange due to black body radiation. And we'll talk about that when we get to nuclear energy and subatomic particles and radiation and stuff like that. But the lower part is blue due to the chemical composition of the flame. Alcohol, I think, is what was used. That's what they said. So what does all that stuff mean with regards to radiation? Well, radiation is a very specific type of transfer. A great example would be microwaves. But before we get into all that stuff, let's look at how this affects ice. So this illustration shows the darker pavement is wetter than the lighter pavement. And that has a lot to do with the darker pavement absorbs more light energy. So remember, we're saying that electromagnetic radiation is light. So if I have the sun over here, here's my sun shining. I gotta get a little more bright. And I'll make it a little more sunny. So I have my sun shining, and so as the sun shines on this, because it's darker, it absorbs more light energy. It doesn't reflect as much. When the sun hits this lighter one, it just reflects off of the pavement. But this one absorbs and keeps the thermal energy. So this temperature here, we'll call this T2 and we'll call this T1, the temperatures of the pavement. Because T2 is darker, that means it absorbs more of the light energy, and therefore the temperature is greater than T1, basically. And so another illustration of this, what's going on is we have a situation like this where as the light goes into something that's a darker color, so here we have black, right? Some of the light goes in and that energy gets absorbed, right? So if you think about it in terms of energy, we have electromagnetic radiation, which is a form of energy, and then that gets absorbed, and then it becomes thermal energy. So it's a transfer from electromagnetic to thermal, and then from there it goes somewhere else. So if it's a lighter color, what happens is that light can be emitted. So the dark one, it absorbs it, and then it can radiate in terms of thermal, right? So it's absorbing light, going into it, right? Then at some point, that extra energy that's in the darker pavement needs to be released. Well, it's dark, so because it's not going to release it in the form of light, it releases it in the form of heat, right? Because this wants to stay in equilibrium. Okay, but now for a lighter color, as the light comes in, right, some of it gets reflected, some of it is absorbed, some of it is retained, and some of it is emitted. So there's not as much absorbed, right? In fact, most of it is reflected right from the beginning, right? So it can absorb the light and then give off light almost immediately, right? And then what is retained is not as much because most of it's emitted. So this too will also experience a little bit of a thermal transfer, but it's smaller. Why? Because most of the light is reflected here. Okay. All right. And this is dynamic, right? There's lots of stuff that changes things. So you could have like dark pavement, but it's in the shade. Like there's other things that attribute to it. This is like generalized. It doesn't necessarily count for every scenario, but in general, that's how it works. Okay, so let's look at another image. This is, and oh, let me write one other thing down. Let me go back one more. So an important thing to remember is that if I have the heat energy, which is energy over time, here's a new equation that is equal to sigma E A T to the fourth. And this is the Stefan Boltzmann that's a T there. It's kind of hard to draw with this thing. Law of radiation. So this is a formula that we could use to, well, you'll have to use it for your homework with regards to radiation. So it's another variation. And I'll let you in on a secret. This is not the only variation of QT. So some of your homework or assignments, you'll have to go back. Sometimes you use the latent heat and the specific heat depending on what type of transfer you have. But QT is QT, right? Q over T, energy over time, is always going to be the same. but we might have to set some things equal and solve for things that we don't know. Well, what does all this stuff mean? Well, sigma, that's the Greek letter sigma, is a constant, and that is 5.67 times 10 to the negative 8. And the units are wild. It's joules per second, meters per Kelvin times to the fourth, right? And this is the Stefan Boltzmann constant, not to be confused with Boltzmann's constant. So that's a number that we use every time. E is just E, right? So we'll talk about that. Remember that E is approximately, let me show you what I'm talking about. So if you go into Desmos, this is like a math review, I guess, without actually reviewing where E comes from. It's a limit on a very special equation. Desmos, oh, I forgot the S. So e to the first power is about 2.72. E is kind of like pi. It's a lesser known number. It's a ratio that we deal with. So if you go, how you pull that up, right here, you have to put e to the x, and then you can just leave it as 1, and this is that 2.72 number. It's kind of like pi. Pi we all know is 3.14, but that number comes from something. It represents something, and I don't know, just remember that e is approximately 2.72. I don't want to go into a big long math lesson about which number. A, of course, is area of the object. So this is the surface area of the object. So that's an area, surface area. And T is the absolute temperature and remember the units for area, this would be meters squared. Right? I forgot to square this, by the way. And then this would be kelvins. But remember, kelvins are going to be, because our temperature is raised to the fourth, that's why we have this here, because it kind of cancels everything out. All right? And so, oh, I'm sorry. E is not, I don't know what I was thinking. It's been a minute since I did this. E is not, it's not this. E is the emissivity, I'll spell it for you, of the material. I'm pretty sure I'm misspelling this word. Emissive. Yep. Sure enough, got the T and the V backwards. Emissivity. There we go. I tried to make it emissivity. Okay. Of the object. So that's like a scalar. Don't worry, we're going to do one in a second here. We're going to do an example problem. Okay. All right. Now let's go to this. So when we look at this image here, a thermal graph or thermal imaging of a part of a building shows the temperature variation. So we can filter light because we know that light contains energy, and we can filter the light and determine the thermal energy of it. So thermal cameras that can do like thermal imaging, they're just really taking in the light that we can't see with our eyes, and then that information we kind of put it into a color so that we could see it, but it really tells us the thermal energy or energy contained in the building. We do it in a way so that the various colors tell us the different temperatures. So in this one, we see that there's a heat transfer to the outside is the most severe, right? Along this path here. This is where we're going to see the most because it's purplish, right? And blue. And so we're looking to see, and then there's other parts there. So you see where the house loses most of its energy, okay? It's coming to the outside of the house. And around the windows, you see that some of the heat energy is coming out there, and on the bottom for some reason. So then let's do one last thing. I got one more equation for you. So the next equation, all objects emit and absorb radiation. The net rate of the heat transfer by radiation, absorption minus emission, is related to both the temperature of the object and the temperature of its surroundings. So we're transferring in or out. Assuming that the object T1 is surrounded by an environment that is T2, the net rate of transfer of radiation is given by an equation. So what am I saying here? Let's think of it like this. T1 is the temperature inside the building, and then on the outside of not T4, on the outside of the building would be T2. And so we're having this energy transfer going from T1 to the outside. And so in order to find the net rate, right, the net rate of transfer, and I'm not going to go into a lot of details as to where this is derived from. We're just going to write it down. Over time is equal to Stefan Boltzmann's constant times the emissivity times the surface area. And now in this case, we would do the difference in temperature. So this would be, you're basically calculating the rate and subtracting the two, right? Okay, so that's how you would determine the rate in which it transfers from the inside to the outside. And really, remember, it goes from the coldest or the hottest to the coldest. So if it's hot outside and it's cold inside because you have air conditioning, you would reverse the process, right? The formula is the same, but the heat would flow into the house is what basically I'm saying. So let's look at an example. So here we're going to calculate the net heat of a person, and this is the heat transfer by radiation. What is the rate of a heat transfer by radiation to an unclothed person standing in a dark room whose ambient temperature is 22 degrees Celsius, ambient 22, and the person has a normal skin temperature of 33 degrees Celsius, and the surface area of the person is 1.5 meters, and the emissivity of skin is 0.97 in the infrared, where the radiation takes place. All right, so how do we do this? Well, we're very fortunate that they gave us a lot of the temperatures, but we've got to convert the temperatures. So remember that T2 is going to be basically the outside temperature, right, which is 22. But if we convert that to Kelvin, it's going to be 295. Remember, it has to be in Kelvin. And then T1 is the skin, which is 306 Kelvin if we add 273 plus the 33. And so then if I wanted to find the transfer rate, I just need to do this, which is going to be Boltzmann's constant times the emissivity times the area times the difference T2 raised to the 4 minus T1 raised to the 4. So if I go to plug the numbers in, this is they were very nice to us in this assignment, or in this example. So, and I'm just going to put QT sub n, or Q sub n over T. Well, what is that? Well, it's always right at the end where this thing screws up. Oh, you're kidding me. Right at the end? Alright, I think I got it fixed. I had to pause the video. I think my computer can't handle it gets to a point where it can't keep up. And it gets glitchy. So this is just going to be the 5.6 times 10 to the negative 8, and I'm not going to write down the units because I don't have enough space. We were told that the emissivity of the skin was 0.97. We were told that the area was 1.5 meters squared, and then the temperatures were 295. Remember, that's raised to the 4th power, minus 306, and that's raised to the 4th power. Anyways, if you go through, it's equal to a negative 98 or 99 joules per second, which is also equal to negative 99 watts. Whew. Seems like a lot, but it wasn't. So that's basically it. And the negative kind of tells you like where the transfer is going to, right? So the temperature of the body is warmer and than the outside surroundings, right? Let's read that again just because the negative sign means something here. The room, its ambient temperature is 22. Now they say dark room because they're saying it's so dark in there, there's no other electromagnetic radiation. In other words, the transfer of radiation is solely based on heat energy leaving your body and being absorbed by the room. The negative 99 means that you're transferring the body, you're transferring the heat away from you, okay? You're going to be colder at the end of this process, right? Your body will generate more heat, but you'll be colder at the end of this process. Does that make sense? Okay, so let me do one last thing. I want to talk about this just briefly. So the greenhouse effect really has to do with how the Earth and greenhouses in general, how the Earth's atmosphere processes the light from the sun, very similar to a greenhouse. The atmosphere is kind of like a window or like a glass window. It's transparent and it allows light to come in. So you've kind of got this atmosphere right here. Whoops. Let's do a lighter color. So right here, we kind of have Earth's atmosphere. It kind of acts like a window where the light can get in. And then these wavelengths are absorbed by the Earth and then re-emitted as IR. Well, IR doesn't really, it has a hard time. IR doesn't, it's very difficult for IR to kind of get past the atmosphere. So what happens is it gets reflected back into the earth. And it's not the atmosphere, it's if we have some sort of greenhouse gas, it just can't pierce through what we call greenhouse gases, and it just comes back. And so this is the whole science behind global warming. But there's a lot of speculation and a lot of debate about how accurate that is, because we've only been processing this information for relatively speaking a short amount of time, so we don't know if the pattern of warming up and cooling down, we don't know if it's a cycle that repeats itself. In other words, the earth gets warm, then it does something to cool off, the earth gets warm, then it cools off, or if it's just the earth was cold and it's getting warmer and warmer and warmer. We're afraid of it getting warmer and warmer because the ice caps will melt, and there's a lot of stuff that will happen with that. And they are melting to some degree. We just don't know if at some point the earth gets colder and then they form again. So we just don't know. But this is what happens.